Okay, so some general notation that we're going to use throughout the course. These are just math symbols that you should know what they mean. So we'll use them. If you do know already, that's great. So we'll use this squiggly equal sign to say that something is approximately equal. We're not exactly equal, but we're trying to approximate something. We'll use this open infinity sign, I'm not sure how to call it. This means that the value on the left is proportional to the value on the right. So that is, they are a constant proportion away from each other. This is very useful later on. We'll discuss gradient descent. We'll see that in many cases proportional to is as good as equal to in some cases. Next, when we write PR capital X equals small x, it means the probability that a random variable x, capital X represents the random variable. PR represents the probability that the random variable x takes on the value small x. We'll use x tilde p to represent random variable x that is sampled from distribution P. E and then square brackets of a random variable x is the expected value of a random variable x. We will use the definition of an expected value, which is the sum of all possible outcomes for random variable x times the probability of seeing that outcome. This is just the definition of an expected value. And of course, this is the definition. The first one is the definition for a discrete random variable. But of course, we can generalize the definition of an expected value to be over a continuous random variable, right? An integral. Same definition. Next, we will use argmax over a variable a for some function f of a to represent the value of this variable a at which the function f, which is a function of a, is maximized. This R, hollowed R, is the set of real numbers. We'll define f, a function mapping elements of set x to elements of set y as follows, right? Just here, it's just a mapping of a function. We'll use a left arrow to represent an assignment of a variable, and intervals will represent with either square brackets or regular brackets to represent interval between two edges, right, A and B. The regular brackets represent an inclusion of the bound, and a squared bracket means that the bound is not included in the range. Okay, let's discuss some of the RL assumptions, or the assumptions that are needed in order to apply reinforcement learning. First of all, we need to assume that we have real-time sensing. So actually, this is an important, so be sure to understand these, because every semester, every year, every instance of this course, we have project proposals that are not appropriate for reinforcement learning. So please take a second to understand what is appropriate, what are the RL assumptions, what is appropriate to be solved with RL and what is not. And we hope, we require you to understand these basic assumptions and to follow them when you apply reinforcement learning. So we assume real-time sensing. At each time step, the agent receives a signal from the environment, which defines the state environment. The state space can be discrete, continuous, or even infinite in size. So on this front, we're not restricting the type of the state, how the state space is defined. Can be as, again, discrete, continuous, or infinite in size. That's fine. You can still apply reinforcement learning. Of course, when we discuss infinitely sized state spaces, or even if they are very, very big, then we'll have to use some deep learning techniques in order to generalize our knowledge. But we'll discuss this later on. But in any case, right, we have solutions to all of these types of state spaces. The signal from the environment might be noisy or incomplete. This is called partial observability. And also it might lead to a distribution over the true state. This is known as a belief state in partially observable MDPs. We'll quickly discuss that later on. Okay, but these all of these variants can be addressed by RL algorithms. However, but in any case, we do need to assume real-time sensing, right? Next, so we also assume real-time actuation. At each time step, the agent can perform an action which somehow affects the environment. The set of possible action is known to the agent, and the action space is not restricted to be discrete or continuous. It can be either, right? So it can be a traffic signal controller, which you change the green to red light. It's a discrete action, right? It's either performed or not, but it can also be robotics with where you control a force for a joint or autonomous driving, where your action space is continuous. Both are fine. We have solutions to handle both cases, right? And we'll discuss those. Next, we have to assume, or RL assumes, stochastic environment. So it doesn't have to assume. We can apply RL algorithms if our environment is not stochastic. But in that case, we'll probably have other AI solutions that will perform better, like automated planning, and there are other solutions. It's not, I would say, you can apply RL, but it's not appropriate to apply RL, okay? What does it mean, a stochastic environment? It means that performing a specific action at a specific state leads to a random new state, okay? So it's not always the same state. There is some distribution over the next state that we might observe. So the new state is randomly drawn with some probability, right? P of seeing a specific next state S prime, given that we are currently at state S and performing a specific action. Okay, so there is a distribution over the next state that we might encounter. We will assume that this distribution exists and is stationary, so our environment doesn't evolve, doesn't change over time. There are solutions to handle that, but for this course we'll assume that it is stationary. But we won't assume to know that, the distribution. So we won't assume to know it ahead of time, but of course once we interact with the environment, we know that the environment, well, it follows some unknown underlying distribution. And we will learn an optimal policy, an optimal behavior, given that that distribution exists, even if we don't know that. Okay, it exists and it is stationary. In some cases, by the way, we might need to, or Vaibhav, let me ask you, do you think that we need to, in order to optimize behavior, to detect the optimal behavior, do you think that we need to learn that distribution?
We need to learn a policy over that which optimizes the distribution.
So you're right, the policy is dependent on that distribution.
Yes.
But my question is, so I'm telling you, to start with, we don't know the distribution. It exists, there is some distribution. But do we need to learn that distribution in order to learn the optimal behavior? So the optimal behavior depends on that distribution.
Yes, but no, we do not.
So, right, and you're right. We could, I'll show you techniques that will optimize the behavior without the need to learn this, distribution, also known as the model of the environment. But there are some solutions, of course. If you are able to learn this model, these distributions, then you can do some optimization on your behavior, some effective optimization, right? You can have some techniques. So these are called model-based techniques, RL techniques. We'll see some of those, but also we'll see later on model-free techniques, where we'll optimize behavior without learning this distribution. The distribution over the state the state space, how the states evolve, the environment evolves.
Sounds interesting.
Okay, yeah, well, hopefully it is, yeah. Next, another assumption is that the rewards are observable. If we won't observe the rewards, well, we'll have an issue. We won't be able to learn. Each transition, state, action, next state, this is what we call the transition. So we observe a state, we perform a specific action, and then we observe a next state. So we assume that each of these transitions has some observable impact on the objective function. This is known as the reward. The reward might be stochastic, drawn from some distribution. However, we will assume that this distribution, again, is stationary. Okay, so we don't change our objective over time. Again, there are solutions, there are some papers that handle that, but we won't go there. Probably you'll be able to find papers handling each one of the edge cases, but during this course we'll try to cover the main RL literature. Okay? So we won't go into most of these edge cases. Okay, moving onwards. There are some more interesting edge cases, but we won't discuss those. You're more than welcome to Google that and follow up on some interesting papers that have different assumptions regarding the reward function. Finally, a very important assumption, and this I think is the most common assumption that is violated in project proposals that we see from students, is the assumption of the Markovian property. What is that? So the Markovian property tells us that the reward and transition probabilities do not depend on states or action visited or performed prior to the current time step. That is, the probability that you see some state in your next time step, given the state in the current time step and the action taken in the current time step, is independent of all of the previous states and action that we saw previously. Okay, so the distribution of next state only depends on the current state and the action that we are performing. And as I said before, this is a bit harder to understand. I'll show you an example in a second, don't worry. I'll show you an example of what does it mean to violate the Markovian property and what does it mean to fix it. But this is very important, and in many cases this is violating the project proposal. So make sure that you understand the Markovian property, and that when you propose, specifically if you have an application-based project and when you propose a specific application, just be sure that your environment follows the Markovian property. Okay, this is very important, else RL-based approaches are, well, less relevant. Okay, so let's see an example, and actually this is the example that Vaibhav discussed or asked about a second ago. So let's say that we are trying to solve or to address, to learn how to learn the optimal controller for a specific Atari game. This is the breakout domain, where there is a ball that hopefully you know this game where you have to, the ball, so you can control the pen here at the bottom of the screen. It can go left or right, and you have to keep the ball from falling down to the bottom of the screen. And the ball can help you break the tiles above, and your goal is to break all of the tiles as soon as possible. And as before, for the Atari domain, the state space here was just the pixels in each one of the screen. And my question is as follows: if we just freeze a single state in the environment, and we'll define the state of the environment based on a single frame from the game, would this be a Markov process? So this ties into your previous question, Vaibhav. So will this be a Markov process?
No, because we don't know the direction of the ball.
Why not? So let's say, so why does it violate though the Markovian process? So remember that the official definition of the Markov process is that the state and action in a given for a given state, and let's say this is your state, is not dependent on the previous state, right? The distribution of the next state that you're going to see is not dependent on the previous state. How is this violated here?
Well, in this case, the direction of the ball would play a matter for what the next state is, and if you don't know that, we can't we wouldn't satisfy the Markov problem. I'm not explaining it right.
Right. No. So that's right. And the next state, if you have a state, the next state, the ball can move well, left, right, up or down, and that will be our next state. And actually, if we would see one state before, if we would see one step before our current state, that will let us know the direction of the vector where the state is moving toward, and that will allow us to better approximate the next state, right? So it is dependent on two states, on 2 pixels here. If we would see the history, we would be able to better approximate the development of the state space. So I will ask, what about if I'll tell you the state, which is just the pixels, plus the velocity of the velocity vector of the ball? Now that would be enough?
Yes, because now I can tell which direction the ball is going to go in, and I can predict its next state more clearly.
Right. So the next state won't depend on previous states, right? Unless you have some velocity to the pen below, but I don't think that's.
No, that's the action. That's the agent.
That's the action. Okay. Yeah. Okay. So yeah, that should be sufficient. So. You know what, we'll get later to how they solve this issue later on. But of course, if you add here the vector, the velocity vector for the ball, then you would have a Markovian state space, or Markovian process, but now you added a feature that is very specific for one of the games, for one of the domains out of all of the Atari games. And in their paper, the solution that they provided, the DeepMinds, the DQN papers, they actually said, hey, we have the same code, we don't have any special feature selection, we didn't design anything specific for one of the domains, we have the same code and it applies for all of them. So they couldn't go into each one of the games and add the specific features that is relevant for that. They didn't do that. They wanted to have a general solution. So they had a different solution. In any case, the velocity vector of the ball here would solve this problem, but later on I'll show you a different solution that they have. Okay, I'll do it just now. So this is the next slide. So how did they solve it? Second. Okay, so how did they change the state space in order for it to be Markovian in the Atari domain in a general way, right? So this is from the 2015 Nature paper. So the way they approached that is to do some processing on the state space. So the state space wasn't only the pixels from the current frame, but they also included the 4 last frames, and this was the state space. So the state in the current time step was defined using the last 4 frames. Okay, that allowed a deep neural network to induce the movement of the ball or movement of any other thing in different domains, right? So it's more of a general solution. They also had some other state processing functions like grayscaling. So instead of RGB, so instead of 3 numbers per pixels, they only have 1. It's just faster to process. So they did grayscaling and also some cropping. So a lot of the frame is irrelevant for playing the game. So they just shrank the size of each frame, also to improve computational efficiency and also to help the network by removing some unnecessary information. Okay, so frame stacking. So the solution that I just provided, or that they provided which is taking the 4 last frames, it's known as frame stacking, is a solution to that problem, but it's not general for any type of non-Markovian situations, right? So it is very helpful in trying to infer, let's say, movement along the screen, but some non-Markovian state spaces might require you to remember more than just the last frame, 4 frames. For instance, if you have a quest domain, like a, what's the name of this domain? Montezuma, right? Montezuma Revenge, where here you control the character and you have to do a specific sequence of tasks in order to complete one section of the game. So for instance, if you need to pick up a key and then go somewhere else to a door and then open it, you have a specific sequence of tests that you have to perform. But these might extend far beyond 4 frames. Well, then again, you might lose the Markovian property. And indeed, in this game, in this specific game, the Montezuma Revenge, this the one that we see here on the left. Right? Yeah, left. Okay, I'm a bit confused. So, in this game, they weren't able to perform actually very well, or better than a human being. Actually, they weren't able to perform better than a random agent, I think, on this game.
I mean, more recent results.
Right, with more tricks.
Yes.
Right, you need so
a lot of tricks. Yes.
You need a lot of tricks in order to solve this game.
One of the most challenging domains, I would say.
Right, yeah.